Effectively, we're on. We're just talking about obviously thermoregulation, depending on the types of situations you're training under. Effectively, I know a lot of this is review from exercise physiology of what we're doing to obviously deal with the excess amount of heat that we're producing and is being exposed to when we're exercising. What we're going to do to adapt to hot weather, which turns out is we're going to sweat more, sweat earlier, and sweat less concentrated, specifically lower amounts of sodium and chloride. And it turns out the more humid, the less wind, the less cloud cover, and the hotter it is, the worse it's going to be. More clouds, more wind, typically better, and lower humidity. And yep, the wonderful plethora of going from heat, cramps to exhaustion and stroke. What we're going to do with both decreasing blood flow to the periphery whenever we happen to be in cold temperatures and then getting into where we're shivering. If it's too cold, now we're risking frostbite. And yeah, wear layers, don't be dumb and stay dry. So it's super exciting. So we've got the gain of heat that we're always going to have from our own body's metabolic production. Now, on top of that, we have our environment, which can be the conduction. So remember, that's the touching a surface, convection, which is going to be a fluid or gas moving over the surface, and then the heat that's being radiated on us. And a great example of radiating heat is the sun on a cloudless day. Now, we naturally radiate heat to the environment. That's what thermographic imaging is about. If what we're touching is colder than us, we're going to be going and transferring that heat to another object, like putting your hand on a cold bench. Convection, obviously that colder air around us, and then evaporation is going to be the loss of that fluid on us via sweat, and that's the major mechanism of heat management during exercise. In fact, that's usually about 80% of it. So, woo! And just another way of looking at it. Well, now, the thing that's fascinating to think about is which we do conduct heat through our own tissues. So that exercising is immediately causing an increased temperature in our actual skeletal muscle. And then that heat is being conducted into our bloodstream, and then it's being convected through the body by our own blood flow, along with still being conducted to the surface. So it's when we exercise, you're going to see this increase in core temperature, but then also increase in peripheral temperature. So yes, we lose a lot through sweating. And of course, as we're going to go higher with our body temperature, we're going to sweat even faster until we get over usually about 104 degrees with the body temperature, because literally that part of the brain is no longer working too well because we've effectively overloaded it with how hot we've now made the body. And so, like anything else, you're trying to be mindful of not overheating. And at the same time, we do have a certain amount that we're losing without even realizing. So we have that insensible water loss, aka this is why at the end of the day, your clothes can maybe not smell so good, even though you don't really remember sweating that much, but you still have a little bit of fluid you're losing throughout the day, every single day. So once again, evaporation is what's really being the major thrust of our heat loss when we're exercising. However, when we happen to be at rest, it's typically more just due to radiating heat out to the environment. And remember, the less clothes we have, so the less insulation, the more effective this radiation is going to be. So we're constantly trying to strike this balance between the energy that effectively our body is receiving and how much it's trying to give off to the environment. Hence, we're trying to strive for effectively what's homeostasis. And like anything else, the more humid it is, in turn, we're not going to be able to use evaporation as much. And you know as well as I do, bud, when it gets really hot in the summer, now we're talking about you're wearing like a 3-pound t-shirt, especially after we did the 9/11 stair climb, how soaked our own clothes was because you couldn't take advantage of evaporation, mostly due to obviously wearing that firefighting gear, which was naturally effectively working as an insulation, keeping that heat radiating in. So we're trying to maintain a relatively consistent body temperature. We're going to use obviously conduction, convection, radiation, and evaporation. And at rest, it's radiation. At exercise, it's evaporation. And like anything else, the higher the humidity is, the worse it is. So obviously when we're exercising, we can really get ourselves to be pretty warm, especially those active muscles where we're talking they can get over 170 or 107 degrees. And that's just the exercising muscle. And like anything, when we increase the temperature a little bit, because now we got a little bit more energy in the system, our actual metabolic processes are going to become more efficient. However, once we start to get over that 40 degrees, now we're starting to really jack up the nervous system. And that's where we can eventually get ourselves into heat stroke, because we completely shut down our ability to regulate, and our nervous system doesn't work because we know think good when we're overheating. So this is being controlled by our hypothalamus, which is getting information from both central and peripheral thermoreceptors. So obviously not just our skin, but inside of our body. We then have our control through our sweat glands, through smooth muscle around arterioles, so we can get more or less blood flow to areas. So when we're cold, we're going to constrict, have less blood to the skin. When we're warm, we're going to vasodilate and have more blood flow to the skin, so we're going to be able to sweat more. We can obviously cause ourselves to shiver, and you can actually have enough cold exposure that you literally start to increase your thyroid hormone production. So this is the basic feedback loop that you're going to see as we go through from one to the other. We have the higher temperature, goes to the hypothalamus. We have the vasodilation of the skin. We then start to sweat more, which is going to bring our temperature down. Then when we're cold, that's where we're going to have the lower temperature inside the body, which is going to tell the hypothalamus to give us that vasoconstriction. So we've got less heat going to the other environment. And we also are going to be starting to shiver, which in theory, hopefully is going to increase our body temperature. So typically when we're at rest, we're talking about 1.25 to 1.5 kcals per minute. Remember, this is just that resting metabolic rate we're talking about. Now, when we're getting an exercise, now we can literally be burning more than 15 calories per minute. In fact, it's pretty easy to get over 15 calories per minute if you're doing something really horrible like Schwinn aerodyne sprints or anything like that. And obviously this needs to be dissipated by all of those thermoregulatory systems in the body. So now we're talking about sweating. Now we're talking about trying to use some better methodology to allow us, or this could be radiation if it's obviously we're not lifting out in the sun. This can be conduction if we're touching a cold surface, and this can be convection if we've got that fluid or gas going over us. So hypothalamus is going to be what's making the major calls after it's getting information from those effectors in our thermoreceptors in our skin and inside of our body, which in turn is going to go ahead and get us to sweat more or get us to shiver. So what's going to go on if we exercise a lot in the heat? Well, remember we talked about this before with cardiovascular drift. We're sending blood not just to exercising muscle, but we need to send it to the skin in order so we can obviously thermoregulate. The body is going to prioritize feeding the muscles. So you can literally start to have an issue with a lack of thermoregulation. On top of that, that sweating is decreasing your plasma volume, which in turn is causing us to go through what's known as cardiovascular drift. And because of this, we are in turn going to go ahead and have a higher heart rate while still maintaining the same cardiac output, which in turn is going to lead much more rapidly to fatigue. So as you'd expect, our temperature is going to go up. We're actually going to be typically taking in more oxygen, just kind of as the way it rolls. And then we're going to actually be using more glycogen instead, because we're just essentially not getting as much peripheral blood flow to our fat cells, and because we're really dilating both to the skin and the muscle. So we're going to have to rely more on glucose. And this also means we can probably increase our lactate because of anaerobic metabolism that we're also going to have to rely upon, because we're not going to be able to keep up that cardiac output. Now, we're obviously going to sweat more, and in turn, this is going to not just cause that loss of blood volume, but also all of those electrolytes, which are minerals. And we're going to have some hormonal releases of aldosterone, and antidiuretic hormone, to help us resorb more water that otherwise would have been released as effectively urine into the kidneys, into your bladder. So as you'd suspect, if you're exercising in the heat, we're going to have higher lactate. We're going to chew through our blood glycogen, or muscle glycogen, much faster. Our heart rate's going to be higher because of that cardiovascular drift. And we're going to see a little bit higher of VO2 demands. So one thing to keep in mind is, as we become trained, notice we're going to markedly decrease our sodium and chloride losses in sweat. However, we are not getting the same effect at all on potassium. So Remember, hormonally, we have ways to get rid of excess potassium, but we do not have that for sodium. So hence, sweating is a good way to get rid of extra salt, like table salt. And so when you're working with individuals, exercise is a good way to help work with high blood pressure, specifically people that are sodium sensitive. But this is also important to keep in mind when you're training athletes, that a low sodium diet is not always a good thing, because they're going to have pretty high sodium losses from that exercise they're doing. Now, obviously the temperature, the humidity, the wind speed, if it exists at all, and then what's going on with thermal radiation. So I doubt you're going to be working out next to a blast furnace or I don't know, a giant bonfire, but like anything else, if you have heat that's radiating upon you from the environment, it in turn is going to be increasing that heat load your body's absorbing. And obviously that's before we factor in the metabolic heat that we're producing. And so as we go further and further into dehydration, initially with heat cramps, you're getting muscle cramps. Now that's where we're going to start to see greater thirst, more sweating, more fatigue. And then we're going to start to see those changes in blood flow to the skin. And that's when heat exhaustion. Then we start getting into the really hardcore symptomology, where literally we can get ourselves into situations of death thanks to heat stroke, because our temperature has gone to be too high and we are being exposed to far too great of a thermal load than what our body can actually tolerate. So depending on what the situation is, when in doubt, always get them into a cooler environment. But the speed at which you need to get their temperature down, obviously, is much more rapid whenever we're talking about somebody with heat stroke, along with we want to make sure we're giving them fluids to make sure that they're going to be able to help rehydrate. And so as we go further and further, now we're really literally risking death once we get over 108 degrees, because effectively we are baking the proteins inside of our brain. And it turns out, after you bake your brain, that's kind of the end of it. So on the flip side of it, still with hypothermia, like anything else, make good choices. Don't exercise in really hot environments. If we have to, exercise only in the very early morning or in the evening when the sun's down. Make sure we're dressed appropriately, make sure we're hydrating before and during and after, and make sure we're aware of symptomology of heat illness. As you'd expect, the lack of fluid administration is going to equal a much greater body temperature increase over time when we're just exercising in the heat. And so make good choices, follow the basics of what we're really looking for. And when it comes to our actual acclimation, getting used to being in heat, which is going to take time, in that you need to be out there for typically about 10 days and slowly increasing exposure to the heat, but also increasing exercise intensity in the heat as the body starts to adapt. And this is going to be because we're going to sweat sooner. So when the temperature starts to go up inside of your body, you're going to sweat at an earlier point. You're going to in turn sweat a greater amount of volume and put less of that sodium and chloride in there. So it's going to be more dilute. So you can sweat more without having issues, hopefully, with cramping. Along with, we're going to be able, thanks to our better job of sweating, not have to move as much blood flow to the skin. So we're going to have more of the muscle. We're going to be able to perform at a higher level. We're going to increase our blood volume, specifically the plasma content of it. And we're going to see our heart rate no longer have to go up as rapidly, because we're doing a better job of thermoregulating. And so because of that, we're going to have a higher stroke volume, and we're also going to manage to maintain our glycogen levels for longer. So once you become heat acclimated, you're still going to see that increase in temperature, but nowhere near as abruptly. And then especially, you're not going to see that massive uptick in heart rate like you would have seen before trying to do steady state in the same heat. So here's a good delineation of how to go ahead and work out in those areas. Make sure that we start off with a much lower intensity and slowly increase it with time. If you try to increase it far too rapidly, obviously you're going to risk injury, and always keep in mind the differences. So if we go from effectively being in Antarctica to going and competing at the equator, figure it's going to take you closer to 10 days. Whereas if you're going from, say, Kentucky in the summer to Florida in the summer, it's going to be relatively similar. You're not going to have as much of a difference. Now, the one thing I'll throw out to my one student here this evening is what would you do effectively to try and mimic heat stress to help someone effectively try to get an idea of what it's going to be like before you even effectively travel from that, say, example, from Antarctica to competing at the equator?
Um, try to simulate maybe conditions. Well, I don't know how if that's possible at where you at before you travel there. So you have an idea, like maybe choosing again, as you said, times of the day, or I don't know, externally putting some clothing wise or things of that sort, maybe.
Yeah, that's not a bad idea, bud, of having them exercise wearing like a lot of clothing. So it's going to kind of mimic that heat stress.
Mm-hmm.
It's not the same, but it's not a bad idea. If you maybe have like a sauna at your disposal, I'm
Mm-hmm.
not telling you to work them out in the sauna, sweet Jesus, but have them sit in the sauna. So it's like, okay, you have to get used to sweating again, being warm, maybe have them do some light stretching in there. Lord knows people pay good money for Bikram yoga anyways. So you're doing something to try and get at it a little bit without obviously having like a full environmental chamber that you could have somebody work out in. So good job. So we want to be exposed to it and we need to be out there long enough. There are people obviously everywhere that never even adapt to the temperature in the summer, never adapt or acclimate, sorry, to the temperature in the summer or the temperature in the winter because they just go from a climate controlled home to a climate controlled vehicle to a climate controlled office with only a couple, maybe a minute transitioning from one to the next. So they never actually have to effectively get these type of adaptations. Now, on the other side, when it's cold, you're going to shiver. And this is just obviously contraction and relaxation of the muscle that's not getting you to do anything. This is going to increase your metabolism. And remember, about 3/4 of all energy you release is just wasted as heat. So that is going to help you warm yourself up, along with you're going to send less blood flow to the skin and then to the periphery, hence why frostbite typically affects your fingers and toes first. Now, obviously, how big you are to start, your body composition, the temperature outside, the wind chill, and then if any of you is submerged in water, are all going to influence your rate of heat loss. And so what you're going to see is notice the body's trying to keep your core temperature, trying to keep everything alive because as bad as it sounds, it's better to lose a limb than it is to lose your brain or obviously something off of your torso. And the greater amount of essentially surface area you have to your body mass, the faster you are going to be losing heat. And this is something to keep in mind that children are going to be losing heat at a faster rate. And on top of that, also depends on how athletes are built. So, you know, the example between you and I, Ihor, is if somebody had to guess which of us is going to be more, has the greater sensitivity to heat loss, it's going to be yourself. And not because I'm obviously part Wookiee, but for the fact that obviously you're taller than I am and you're lighter than I am. So you have a greater amount of surface area simply just because you're taller and you've got longer limbs. Whereas I obviously outweigh you. So my mass is greater when we're looking at that surface area to mass ratio. Does that make sense?
Yep.
Awesome. And then it's also interesting is typically women actually have a a lower area to mass ratio compared to men. So actually your average female is better at thermoregulating in cold environments than men are. And also your average female has a higher amount of body fat. So as you'd suspect, if you happen to be exercising in colder water, you're not going to have as great of a body temperature increase. And so this is actually fascinating because this is maybe from equivalent of like doing kind of triathlon work. You see if you're doing that triathlon in warmer water, you're going to see a much greater increase in body temperature because you're using convection and it's not really cooling you down anywhere near as much as the colder water. But then once you get out in that air, so now you're obviously probably a little bit wet still, and you have major convection of the air around you, and you can see that temperature gradient that's much greater. So depending on how much of you is in cold water and effectively how cold that water is, it gives you an idea of how long before you can really expect effects of, negative effects from that cold exposure. You know, thankfully, if it's warm enough, you can effectively hang out there forever as long as you're moving. But if you're stuck and not being able to move, now you're getting yourself into major issues. Now, the reason for this is because it turns out, once again, all your tissues like to work, not just when optimal pH ranges, but optimal temperature ranges. And your muscles are not going to work that well. And obviously, once we get down further, now our muscles aren't working, or we have a bigger risk are working as well. So our shivering effect's not going to be as great. We're not going to actually do as good of a job of freeing up fatty acids because we're not getting blood flow to the periphery, so those adipose cells again. And so we're going to have to rely more on glycogen, which we're going to be burning through at a much faster rate, along with our blood glucose. So you're really talking about fatigue comes on pretty quickly. If we're getting below 94.1, we literally completely lose our ability to regulate body temperature. This is where you have, like, I believe the term is like paradoxical, it's effectively you no longer feel cold. So you sometimes find people that die of hypothermia effectively naked because they hit a point where they literally don't feel cold anymore. So like, why am I wearing all this snow pants and this burqa and everything else? And let's take this gear off and be comfortable. And unfortunately, they succumb. And yes, you can literally vasoconstrict so bad to that skin that then the skin starts to freeze and die. And that's freezing, obviously, once it starts to get into your extremities of your fingers and toes, it's really easy to lose them to the cold. So you can have a slight increase in your metabolic rate due to being cold, not going to be that big of an effect. You do toughen up to a certain extent, as in you kind of get used to it, but it's still nothing that you're really going to adapt that much to. And like anything else, it's getting exposed to the cold along with wearing appropriate clothing. So that way you've got layers, you've got things that are moisture wicking. So that way, if you do start sweating, it's not going to then, as soon as you stop, really freeze you out pretty quickly. That you have take off layers when you warm up and put them back on as you cool down. So this one's relatively easy and straightforward. It's a lot of stuff that we've already obviously covered before in undergrad phys. What questions, comments, concerns do you have for me, Ihor?
I have one question, maybe a couple, but with cardiovascular drift, could you, if I understand it correctly, it's when there is a change in heart rate because of that sweating and loss of fluids, right? And then the body tries to compensate for that loss of blood plasma because the blood becomes more viscous, right? And so the heart rate increases to maintain cardiac output to the muscles, right?
Yes.
Okay, so that's pretty much the cardiovascular drift, because I think I got it confused with something else.
Yeah. When it comes to cardiovascular drift, you sweat out enough blood that your blood's more viscous, so you don't fill the heart as well each time. And because of that, your stroke volume is a little bit lower. So the only way you can offset that loss in stroke volume is to increase.
Okay. Yeah, I think that was it. That was actually the only one question that I had.
Cool. Wow. Killing it, man. Awesome.
Yeah.
Well, we're good.